So let's go hands-on and explore how max pooling can both make our CNNs run faster and more simply, which allows us to run it for longer and get better results out of it. So back into section 11 here in your Jupyter Notebook, let's go into Image Classification CNN Revisited and play around with that. All right, so we're going to improve on our model in a couple of different ways. So first of all, we're going to add multiple layers of convolution. Now the idea here is that as we progress through more convolution layers, they can learn higher level features. So by stacking the same convolution 2D layer on top of each other, we actually allow for more deep learning to happen at the CNN level itself. So that's trick number one that we're going to apply in this. And if you look at the actual examples that come with Keras, that's something that they do pretty consistently. So although it adds more complexity to the deep network, it is worth doing. So that's the first thing we're going to do. The other thing we're going to do is add a max pooling 2D layer in between each layer. So after our first pass at convolving, we'll do a 2x2 max pooling 2D layer to reduce our 32x32 images down to 16x16. Then we'll do it again to get us down to 8x8. And by the end, we're down to just 4x4 images. Now this helps performance a lot since we end up with a lot less data to process. And since we're identifying higher level features as we go up the topology of our deep neural network, it makes sense to use lower resolution images as we go higher up, since that detail becomes less important as you're looking at higher level features. And we're also going to add dropout layers in here like we did before to prevent overfitting. So basically we're going to use more layers. We're going to stack convolution layers on top of each other, and we're going to do max pooling at each level to try to create a more optimal model here for CNNs. And let's see if it works. So let's take a look at how we're setting up our topology this time. And you can see this is much more complicated than before. So instead of a single convolution layer and a dropout and flatten, we're actually setting up three different ones of these individually here. So we have a convolution stage here, a 3x3 convolution, and that gets stacked onto another 3x3 convolution. Like we said, that can help it pick out more complicated patterns. In particular, that's useful for picking up non-linear patterns that may exist within our data. So by doing a convolution on top of the convolution, we can pick up more complicated patterns that might exist in that source data. We will then do a max pooling layer on top of that with a 2x2 kernel. So that will reduce each 2x2 area of the image down to a single pixel, choosing the maximum pixel value at each stage. Then a 25% dropout to prevent overfitting. Then we do it again. This time we're going to do a 64 neuron convolution layer with a 3x3 kernel again. Stack that on top of each other again do max pooling 2D and another dropout. So again, by stacking this convolution layer here on top of this convolution layer, or this more complicated layer that's sort of its own little entity, we can learn higher level features on top of things. We'll do it one more time with another 64 neuron 3x3 convolution layer stacked on top of itself. Again, do max pooling again. So now by this time we're down to 8x8 images. Again, a 25% dropout to prevent overfitting. And then we'll flatten it all down, feed it into our 512 flat layer of hidden neurons, do a 50% dropout again, and finally boil that down to 10 output neurons from which we can choose our final classification value from our neural network. Whew. All right, let's kick that off. And as we did before, we'll prepare our data and visualize it. So same data set as before, same shapes, and we can see that it's unchanged. These are the same sample images we looked at previously. So again, we have these images that have given correct labels. Our job is to predict the right labels and actually say that that truck is a truck and that horse is a horse and that ship is a ship. And again, as before, we will normalize our data. Neural networks like low numbers that are, centered around 0 ideally, but we'll at least scale down our 0 to 255 color data down to 0 to 1 scale by dividing everything by 255. And we'll compile our CNN again. The only difference here is that create model is returning that more complex model this time around that's doing multiple layers of convolution and applying max pooling 2D at each step to try to reduce things down. And we'll do a model.summary to make sure that we have what we asked for. Yeah, it's a lot more complicated, right? So again, we have 2 convolution layers, max pooling dropout, 2 convolutions, max pooling dropout, 2 convolutions, max pooling dropout, flatten it down into a dense layer, and then do another dropout, and finally get down to our final classification. So let's actually train this neural network now. Now, even though it's much more complicated, because we're using max pooling, we shouldn't be dealing with that much more data than we were before. So let's kick this off and see how long it actually takes and what the results are this time around. All right, looks like that finished. So let's take a look at the results here and how long it took. 106 seconds, so that's interesting. So it ran in about half the time as before, even though it's a much more complicated model. And that's really the power of max pooling. By reducing that data down, every time we do a 2x2 max pooling layer, we're basically taking the square root of that data size. So it really boils things down and produces a lot less data that we need to look at each stage there. So very big impact on performance here. Let's take a look at the resulting accuracy and see if we paid a price there. No, we didn't. It's actually more accurate than before. So that additional complexity that we added to the model actually yielded a more accurate deep neural network, and one that ran in half the time. So pretty cool, all right? So originally we had about 60% accuracy. Now we're up to 64%, almost 65% even with all those max pooling layers that were removing quite a bit of information and a lot of detail along the way. So with max pooling, we sped things up considerably, and by improving our topology, we didn't have to pay a price in terms of accuracy or speed of convergence. So we made up for that loss of data through a more clever topology to some extent. And the really good thing is that because we got things running faster, that means we can run more epochs in the same amount of time and get even better accuracy. So let's try it. Let's go for 50 epochs this time and see how good it can get. Let's go ahead and click on this. The only change here is that we're changing epochs to 50, and we'll print out the time that it takes for that as well. Let's kick that off and we'll come back when it's done. All right, looks like that finished, and it was a reasonable amount of time. Let's see how long it actually took. And man, it's getting warm in here. That really put my computer to work there. 511 seconds, so you know, about double what it took to do 10 epochs without all the max pooling that we did before. So 50 epochs there that we ran, and let's take a look at what the accuracy was doing. Looks like we did in fact converge, so it was kind of like going back and forth between 0.7 and 0.8 by the end there. So definitely enough time there to converge, and hopefully didn't overfit too much. Cool, so let's actually measure the results here and see how much better it did. Hey, 80.9%, that's almost 81%. That's a lot better actually. So we did get quite a bit better by running those 50 epochs instead of 10. Let's take a look at the resulting model that we got back here and sample it with some images here that we actually got wrong. Same code as before, we're just going to walk through the first 100 test images. Compute the actual predicted category by taking the output of our neural network, running it through with predict, and then calling argmax to select the category with the highest probability. Also call argmax on the one hot encoded label data. Compare the two, and if it's not the same thing, we'll print out the prediction versus the label using our lookup table of class names and show the actual image that we got wrong. All right, so here's an airplane that we thought was a cat. Yeah, I mean, that is kind of a cat color. If you use your imagination, I could imagine that being cat ears and a cat nose, so forgivable, you know. I see a plane, but it's a very specific fighter jet that you wouldn't necessarily know about. This deer dog here, apparently we thought it was a deer when it's a dog. Again, very indistinct image here, so the way it's standing is kind of a deerish pose. Can't really see the head too much. So I can forgive that one. Here's another deer-dog mix-up. And yeah, the way it's standing, it's kind of a deer color. Those could be antlers as well as ears, just due to how low resolution this data is. So is that a cat or is it a dog? You know, looking face on like that, kind of hard to tell. Cat or a bird? Well, that's definitely a funny-looking bird. So yeah, I mean, you can understand. I mean, come on. You know, I mean, how would you know that's an airplane unless you knew what a stealth fighter looks like, right? So anyway, that's you can see that the ones that it's getting wrong are a little bit more challenging, but I think it's pretty darn impressive that it's doing as well as it is. I mean, 80% accuracy on such low resolution images, we don't have a lot to work with here. And we're making no effort whatsoever to normalize this image data. We're not making it the same colors and the same scale and the same perspective. The neural network has to figure that all out by itself. So it's picking up on these patterns of what makes a bird all on its own. We're not giving it any predetermined knowledge about that at all, you know, well, apart from the training data, of course, but the neural network itself is just what would be going on inside your head. It's really, really exciting stuff, if you ask me. So yeah, I mean, the ones that are tripping it up are pretty strange examples overall, and you can see how it got confused by some of them. But, this is even just the beginning. There are predefined CNN topologies that you can get from model zoos that do even better than this. So as impressive as I think these results are, we can improve on it even more. So let's keep on going and do even more with CNNs and image recognition and see how that can apply to the world of self-driving cars in particular.